Hey everybody, hope you're all doing well, staying healthy and keeping positive there as we continue our remote learning here, getting ready for our AP test. Just a reminder that that has been pushed back to sometime between May 11th and 22nd. I think ours was supposed to be on the 7th, so we will get at least a little bit extra time. So that's nice. But yeah, and remember that's all going to be online. I think they said they're going to give about 45 minutes and it's going to be five free response questions, and that's the whole thing. Okay, so the next thing we need to talk about here is rotational kinematics, and some of you might be not very happy to see the word kinematics come back here, but it's really not too bad. I put in the next slide, and I'll say it again, that some students do find this stuff to be kind of tricky, so I'm gonna do my best to be thorough and take my time, but not drag it out either, because no one likes that. So if you're finding yourself getting a little bit lost or anything like that, what I would do is I would start doing this video in chunks and make sure that before you move on to the next thing that you really understand what we just talked about before that, and do the homework in chunks too. And that I think that'll help. But I'll try to be as thorough as I can and efficient and just as clear as I can. So let's go ahead and get to it. So a quick review. Kinematics was the study of motion, right? That's what kinematics is, studying motion. The measurements involved in kinematics, the things that we were always trying to figure out or calculate, we were always trying to figure out displacement, which was a change in position. So where did you start? Where did you end? How far apart are those 2 points? Velocity, and remember velocity is just speed, so how fast are you going? But direction also matters, so north, south, east, west. Same for displacement, direction matters. Acceleration, change in velocity. How did your velocity change? Are you speeding up? Are you slowing down? And how quickly are you doing that? And time. So if you go back to kinematics, look at your kinematics notes. These were the things that we were always trying to find. We were trying to figure out time, acceleration, velocity, or displacement. Okay. Rotational kinematics will basically measure the same things, but just in a circle. Okay. Same stuff, just in a circle. And I already said this once, but it's so important that I'm going to say it again. Many students find rotational motion to be tricky. Something that will be a big help is to connect rotational to regular kinematics because they are extremely similar. And that is absolutely true. We're still measuring velocity. We're still measuring acceleration, time, and displacement. We're measuring the same things, just in a circle. Okay, and so like a lot of the equations and the definitions will be very similar, if not the same, as when we did this in regular kinematics. Okay, so just take a moment to breathe and realize that you've basically done this already, just with different symbols. Okay, and now we're just going in a circle. Okay, so angular distance in a circle. One very important thing to remember from geometry is that the distance around a circle is called the circumference. And we know how to calculate the circumference. The circumference, so the distance around a circle, is equal to 2 pi r. Remember, r is the radius. That's how far the edge of the circle is from the center. Just like this red line up here in the corner. That's a radius. One revolution is one trip around the circle. So if you talk about a revolution, if you go one revolution, you went around the circle one time. Kind of like this right here. I'm going to see if I can maybe do it again. There you go, around the circle. All the way around once, one revolution. Circular distance can be measured in revolutions. Okay, that is a real measurement for how far around a circle you have gone. What we're going to use to be the symbol for circular distance, we used to have delta D. Now we have delta theta, and theta stands for an angle here. And circular distance can also be measured in degrees or radians. When it comes to all this motion going in a circle, degrees is not very convenient, so we'll never use that. We're going to use both revolutions. We'll be using both revolutions and radians. So we will measure them 2 ways, it's basically just like using meters or feet, right? Just measuring the same thing, just two different units, radians and revolutions. We will need to know how to convert between those. 1 revolution is equal to 2 pi radians. Okay, so one time around the circle, that's 2 pi. Same as 360 degrees. 1 revolution, 2 pi. They're all the same thing, okay? One thing we need to notice here is that these distances do not tell you how far someone might have walked if they were to, say, walk on a circular track. Like you wouldn't be able to say, I walked 500 meters today, or I walked a mile today. We're not saying how far you went. It has nothing to do with actual distance like that. When we talk about circular distance, it has nothing to do with that. It is purely how many times have you gone around the circle? 1 time, 2 times, 3.5 times, 0.25 times, whatever. How many times have you gone around the circle? So, but we do need to be able to connect those two things, how far around the circle you've gone to your actual distance. For example, Jack walks around a circular track 8 times. How far did he walk if the radius of the track is 5 meters? Okay, so here's our circumference, 2 pi times 5. The radius of the track is 5. So 1 time around the track, that distance is 2 pi r. 2 pi times 5. Same equation as up here. Circumference equals 2 pi r. Just geometry. That's 1 time around the circle. Okay, so that's 1 time around the circle. How many times did he go around the track? He went 8 times. So we just take that and multiply by 8. That's 80 pi meters. So he walked 80 pi meters. Maybe you don't like that we leave the pi there, so you put 80 times pi in your calculator, you would get 251.3 meters. So how far did he walk if he went around the track 8 times? He walked 251.3 meters. Okay, now that's angular distance. Let's move on, and displacement. Let's move on to angular velocity. And I put the regular velocity equation up here just to remind us what velocity means. This seems a little bit intimidating, but remember, it's still velocity. Velocity is velocity. It's distance over time. How far did you go, and how long did it take you to do it? Were you going 30 miles an hour or going 60 miles an hour? But remember, we're not measuring distance as in miles. We're just measuring how many times did you go around the circle, and how long did it take you to go that many times around the circle. So, angular velocity answers the question, how fast is it spinning, or how fast is it going in a circle? The variable we're going to use here is this cursive W. It's a Greek letter that's called omega. Angular velocity can be measured in revolutions per second, or it can be measured in radians per second. So, how many times did you run the circle, or radians? And we do need to be able to convert between those two things. And I'll do an example over here in just a minute. We do need to be able to convert between revolutions and radians. Okay, the straightforward way to calculate angular velocity is just by definition. Velocity is distance over time. This is velocity, and it's basically distance over time. It's still the same thing, except instead of measuring meters, now we're measuring revolutions or radians, okay? How many times you go around the circle divided by how much time did you spend doing that. Velocity is distance over time, or angle over time, revolutions over time. So here's an example. A car drives 10 revolutions around a circle in 2 minutes. To find this angular velocity, just divide distance by time. 10 revolutions divided by 2 minutes is going 5 revolutions per minute. Okay, so here's a conversion example. An object is traveling in a circle at 7 revolutions per second. What is the angular speed in radians per second? So since each revolution is 2 pi, you just multiply. Omega is 2 pi times 7. We had revolutions. Each revolution is 2 pi. And how many revolutions do we have? 7. Okay, so 2 pi times 7 equals 14 pi radians per second. Or if you want to multiply these out, 14 times pi, about 44 radians per second. You want to be able to use both of these, either with the pi there or without the pi there. Both Brain Genie and AP will use either one at any time. Okay, so you never know. It's not like they're going to stick to that one or stick to the other one. You got to be able to use both. So just to recap here really quick, this example down here was an example of how to use the straightforward equation, the definition of velocity, angular velocity. The example in the box is an example where we already have the angular velocity and we just want to convert between revolutions per second and convert that to radians per second. Okay, and you want to be able to do all this stuff. You want to be able to do this backwards too. So if I give you if we give it to you in radians, you should also be able to go back to revolutions. Instead of multiplying by 2 pi, you would divide by 2 pi. That's all you got to do. Make sure you know how to do both directions. Okay, we do have another way to measure angular speed, and that is to use the period. So if you don't remember what a period is, I'll remind you right now. The period, we did this way back in waves, right? And a period is the amount of time that it takes to go through one cycle or one full time around. So how long does it take you to go around the circle just one time? Okay. And this makes the distance, we're basically using the same equation that we just did up here, omega equals delta theta divided by t. But the nice thing is this makes the distance easy because it's always going to be 1 revolution on the top part of the fraction or 2 pi radians, depending on how you want to measure it. Do you want to measure it in revolutions? Well, then you put 1 on the top. Do you want to measure it in radians? Then you put 2 pi on the top. And then you just do distance divided by time, like we did the first time. So here's an example. It takes a marble 1.7 seconds to go around a circular track once. Find the angular velocity in revolutions per second and radians per second. Okay, so revolutions first. 1 revolution on top. We did 1 revolution. Divided by that took us 1.7 seconds. 1 divided by 1.7 is 0.59 revolutions per second. So that's revolutions per second, or you could do it 2 pi radians divided by 1.7 seconds, because 2 pi radians is the same as 1 time around the circle. So 2 pi divided by 1.7 equals 3.7 radians per second. Okay, these say the same thing, just with different units. You could convert from the first one to the second one, just like we did up here. Just multiply by 2 pi. So if you take 0.59, multiply by 2 pi, you will get 3.7. And you could go backwards too, by dividing. Okay, angular acceleration. This answers the question, is it spinning faster or spinning slower? And how quickly is it changing its angular speed? Okay, the variable we use for angular acceleration is alpha. It's this like funky looking A here. Again, another Greek letter. We can measure this in revolutions per second squared or radians per second squared. Again, we need to be able to convert between revolutions and radians, but notice the seconds squared on the bottom is staying the same. So the only thing we're changing is revolutions to radians. So you still do the same thing. It's either multiply by 2 pi or divide by 2 pi. That converting between them, you still need to know how to do it, but how to do it does not change. You do the same thing, multiply or divide by 2 pi. Okay, we can calculate this by definition. Acceleration is how much does your speed change divided by time. It's the same thing, same definition we use for acceleration for regular kinematics. You change in speed divided by time. It's just that this time we're using the circular speed, the angular speed, the rotational speed. All those mean the same thing, whatever you want to call it. But acceleration in a circle, the angular acceleration is the angular, how much does your angular speed change, and you divide that by time. So here's an example. A centrifuge is spinning, changes speed, changes speed from 9 revolutions per second, and it speeds up to 32 revolutions per second in 6 seconds. And we want to know what is the angular acceleration. So at first it was going 9 revolutions per second, then it speeds up to 32 revolutions per second, and that takes 6 seconds to do that. So the angular acceleration, how much did the speed change from 9 to 32? How much did it change? It changed by 23 revolutions per second. And then we divide by the time, 6. 23 divided by 6, you get 3.83 revolutions per second squared. Okay, same thing you would do if it was regular velocity, just a little bit different units. Okay, a couple important things to remember here. We need to remember that displacement, velocity, and acceleration are all vectors, so direction matters. For example, if something is spinning at 10 revolutions per second clockwise, slows down, stops, and speeds up to 10 revolutions per second counterclockwise, so first it's going 10 one way, and then it switches up and starts to go 10 the other way, the change of velocity there is 20 revolutions per second, or negative 20 revolutions per second. Depends on which way you make positive. It's totally up to you. It's like going from negative 10 to 10. To get from negative 10, you have to go up 20, right? And so direction still matters, even though we're going in a circle. All right, here are the rotational kinematic equations. First, before I give you the rotational ones, I want to remind you of the regular ones. Okay, so this is what we spent plenty of time on, was these equations right here. We actually had one more, but I'll get to that in a second. So these are the equations that we had. If you look back at your kinematic equations in your notes, this is what you should see. Except instead of this x minus x0 here, we use delta d instead, but they mean the same thing. Okay, so these are the regular equations. Let's look at the rotational equations. Here they are. And the thing I really want you to pay attention to here is that they are very similar, super similar. In fact, they're pretty much exactly the same, except the only difference, for example, is that our regular velocity v is not a v anymore. Now it's swapped with the omega, but they're both, it still means velocity. One's just going in a straight line, and this velocity is going in a circle. And so, and I mean, this work, it goes the same for the acceleration and the displacement. This a is just swapped with the fancy a, and t stays the same. Time is time, that doesn't change. But if you look at this equation, it's literally the same thing as that equation. Your final velocity is equal to your starting velocity plus at. Your starting velocity is equal to, your final velocity is equal to your starting velocity plus at. They're the same equations, just different symbols, okay? Just different symbols. And so that's kind of what I was talking about earlier, that this stuff is super similar. It can be a little bit easy to get tripped up on this stuff, but take a deep breath and just think, no, you've done this before. You can do this. It's just different symbols, really, it is. That means the process for solving rotational kinematics problems is the same. So the way we attacked these problems when we did kinematics the first time, you're going to attack these ones exactly the same way. Some of, no, I don't want to say that, but they're going to be easier. Let's just not say that. Yeah. You just go, whatever the problem's asking you to do, whatever you would do in the regular stuff, you do the same thing in the rotational stuff. Okay, so I kind of mentioned this earlier. I know we used 4 equations before. The reason I'm only using 3 of the 4 is because these are the 3 that is in the AP handbook and in the course manual. So since this is what AP has, this is the only 3 we're gonna stay with these 3 and just stick with those. Okay, another thing. Remember that the little 0 down here remains initial or starting. So omega 0 is your starting velocity. And then the plain omega without the little 0 is final velocity. I think in class we used I and F. They don't use I and F. I just want to remind you, this is what they're using. They're using 0 for the start and then just nothing for the final. So if it doesn't have the little 0 right there, that's the final velocity. I also mentioned this. I remember that we used delta D instead of this x minus x0 here. The x is just there instead of d to remind you that we used a d instead of x and y. The reason that they use an x instead of a d is just to remind you that x and y directions have to be separate. So when we did these before, you can't just measure on a diagonal. You had to do x's separate and y separate, and we remember doing that. And rotational is its own thing anyway. There's no x and y to rotation. It's just this. It's just this. Last note here on that, unless they specifically give you a start and end position, we can always set our starting point to 0. So for example, if they don't tell you where to start, you could just, for theta 0, you could just put theta 0 equals 0. Because they didn't tell you where to start. So start at 0, because that makes your math a lot easier. And then you're only left with the regular theta anyway. And you could basically think of the regular theta. If this one's not even there, you could think of the regular theta as the delta theta anyway, or your delta D. Okay, so basically you could just be like, oh, well, this is going to go away because we're just going to call that 0 if they don't tell us where to start. And here's your delta theta, or delta D. So they're pretty much the same thing. Okay, so I'm going to do one example problem here for you. I don't want to do a ton of them because it's just going to take a long time. But I will do one where we use those variables and those equations. So an object is initially traveling in a circle at 300 revolutions per minute. If it then completes 250 revolutions in the next 30 seconds, what was its angular acceleration? So we have initial velocity, we have angular displacement, it went 250 revolutions, that's angular displacement. The velocity, that's the 300 revolutions per minute. We also have time, because they gave us 30 seconds, and we need acceleration. We need the angular acceleration. So the equation that we need to use based on what we have and what we need is this one right here. Theta equals theta 0 plus omega 0 t plus 1/2 at squared. The 1 plus 1/2 at squared, I mean, it looks the same as it did before, almost. It's a fancy A now. Okay, so for the first thing we need to do is convert 300 revolutions per minute to revolutions per second, because they gave us the time in seconds, but they gave us the speed in revolutions per minute. Purposely used an example where we had to convert this. We need to change minutes to seconds so that all the units match. Okay, so we're going to do 300 divided by 60, and that gives us 5 revolutions per second. So you might be wondering, how did he know to divide? Obviously, we know that there's 60 seconds in a minute, but how did he know to divide instead of multiply? Well, okay, if you can go 300 times around in a minute, how many times can you go around in a second? Is it going to be more or less? Well, definitely, I can't go as far. If I only have 1 second, I can't go the same distance that I could in a minute. So it's got to get smaller. So that's how I knew how to divide. You can't go as far. How long can you go in a second? How long can you go in a minute? Obviously, you can go farther in a minute than you can in a second. So make it smaller. Okay, now plug in and solve. They didn't tell us where to start, like they usually won't. And so we can make theta 0 equal 0. We're going to start at 0. So I'm going to take, all I did was take the numbers up here that I was given and put them in this equation right here. I didn't want to copy this equation down here because it would just start to be a lot. Okay, so we started at 0, and then we went 250 revolutions. So that goes in the theta spot because that's our angular displacement. That's how many times we went around the circle. So that 250 goes right there. We started out by going 5 revolutions per second. So that 5 goes there. This is our starting speed. Our starting speed was 5 revolutions per second, so there it goes. And then t, our time is 30 seconds, so that goes in the t spot. I changed the 1/2 to a 0.5. 0.5 is 1/2, but usually when you're doing things in a calculator, it's a little bit easier to use 0.5 instead of the fraction 1/2. So that's why I did that. A is what we're looking for. We don't know A, so I just left it. That's our variable. And then again, we have another t. This t is squared. We already know our t is 30 seconds, so we got 30 squared. So 250 equals 0 plus 5 times 30 plus 0.5a 30 squared. Now, all I'm going to do on this next one is I'm going to drop the 0. We don't need it. I'm going to do 5 times 30, and I'm going to multiply these numbers over here. So I'm going to just multiply in the middle and on the end. Okay, 5 times 30, that's 150. If you do 0.5 times 30 squared, you get 450. If you're trying to figure out, if you don't get that in your calculator and you're trying to figure out what you did wrong, remember that we need to do exponents first. So 30 squared is 900, and then half of 900 is 450. So if you're doing this in your calculator and not getting 450, try doing it in 2 steps. Square the 30 first, then multiply it times 0.5. Okay, now we have a really simple equation. This is algebra 1 stuff. We should all be able to solve this equation right here for A. We got A, we're trying to figure out what A is. Let's do it. We got to subtract 150 over to the other side. So 250 minus 150 is 100. Now we have 450A here. We need to get A by itself. So how do we get A by itself? We got to divide by 450. So A is 100 divided by 450. And when you do that, you get 0.22 revolutions per second squared. Okay. So, like I said, this stuff is literally almost the same equations. It's almost the same stuff as when we did this with regular kinematics. Just the units are a little bit different. The revolutions and radians instead of meters, and the symbols are different. But we've done this before. We can, if I gave you all these numbers just with regular in a straight line, regular kinematics, I would definitely expect that we all be able to do this problem. Okay, so don't be too intimidated. It's the same stuff, just different symbols, different units. Okay, excuse me. The two are connected though. Rotational and regular kinematics, they are definitely connected. So let's say you run one lap around a circular track and you want to know how fast you are running. Okay, so and you don't want to know angular speed. You want to know your actual speed. Were you running 8 miles an hour, 10 miles an hour, 12 miles an hour? How fast were you running? Okay, so we're looking for regular v here, and v is velocity is distance divided by time. Okay, what distance did we travel? Well, we went around the circle one time, right? So how far did we go? How far we went is the same thing as the circumference. So our delta d is 2 pi r. That's the circumference of a circle. That's how far we went, 2 pi r. And so I'm going to take this and I'm going to put it in that d spot, the delta d spot. So that means that v is equal to 2 pi r over t. All I did was take 2 pi r and put it where delta d is. But hold on a second. If we look at this a little bit closer, 2 pi, that's an angular distance, right? 2 pi radians, that's one revolution. If we go way back to like the first, second, and third slide that we talked about this stuff, 2 pi is angular distance. And we only ran one lap. So t, in this case, represents the period. We went around one time, right? So that means t is the period. We already talked about on the velocity page how the second way to calculate velocity, angular velocity, is 2 pi divided by the period. We didn't, if you look, it was at the bottom of the page on that one. 2 pi divided by the period is your angular velocity. That's omega. Okay, so let's look at v again. All I did was take the same v equation, but now I made r kind of separate. So we have 2 pi over t by itself here, and well, 2 pi over t over here is 2 pi over t. What is 2 pi over t? That's omega. So I can take this 2 pi over t and just change that into an omega. So this gives us a really important equation right here. V is equal to omega times r. This is how we get from regular speed to circular speed, or angular speed, rotational speed. Okay, it's actually a nice little simple equation. Your straightforward speed is equal to your angular speed just times the radius. That's all you got to do is multiply by the radius. Okay, so and this is how you get back and forth between the two kinds. And I'm going to do an example where you need to use this right now. Okay, so I just put that equation right up here. V is equal to omega r. Put that equation up here. An object starts from rest and begins moving in a circle with a radius of 5 meters. After 12 seconds, the object has a velocity of 40 meters per second, and I want to know the angular acceleration, not the regular acceleration. I want to know the angular acceleration. Okay, well, our delta v, or how much did our regular speed change? It changed by 40 meters per second because the object started at rest. We went from 0 to 40, so how much did it change? It changed by 40. Okay, so now we're going to solve for and calculate delta omega. So I'm going to use this equation right here. But instead of having v by itself, I already know v. We need the angular v. So all I'm going to do is take this equation and get omega by itself. It's all I got to do is to do that, to get omega by itself, all you got to do is divide by r. And so what do you get when you divide by r? You get v over r to get your omega, v over r. Well, how much did our speed change? It changed by 40. Divide by r. I told you the radius of 5 meters. So 40 divided by 5, that's equal to 8 radians per second. And I do want to make a very important point right here. Whenever you use this equation right here with v and omega together, this needs to be in radians per second. It should always be in radians per second when you're using this equation. All right, so now that we know how much our speed changed, then we just use the definition of acceleration. Acceleration is your change in speed over time. In this case, our change in angular speed divided by time. So how much did our angular speed change? We just did that. That's 8. How much time? 12. So 8 divided by 12 is equal to 0.67 radians per second squared. Okay, I think this is the last thing we need to talk about here. Centripetal acceleration. And I'm kind of gonna give you something to imagine here and kind of guide you into what centripetal acceleration is here. Let's say you're in a car traveling at a constant 10 meters per second in a circle. And let's say that circle has a radius of 4 meters. Okay, so you're going constant speed. You look down at the gauge in the car and it says you're going at a constant speed. The needle's not going up or down. Okay, you're going at a constant speed, but you're going in a circle, and that circle has a radius of 4 meters. So my question is, can the car be accelerating even though the speed is a constant 10 meters per second? Okay, just think about that for a second. Speed is constant, but we're going in a circle, so is there acceleration? And the answer is yes, because acceleration is a vector. And I know I brought this up one other time earlier in this video, and that means when we're talking about vectors, it means direction matters. So even though the speed is constant, the direction is changing, right? The direction is changing, and that does count as acceleration. Your speed is not changing, but the direction is. So you are still accelerating because direction matters. Okay. Here's the next question. Which way are you accelerating? The answer to that question is towards the center. You are accelerating towards the center, which is why you're going in a circle, because you're always trying to get to the center, but you just can't get closer. This is called, so this acceleration is called centripetal acceleration. The word centripetal literally means center seeking or towards the center. So this is an acceleration towards the center. It has an equation that goes with it. C with a little c right here, c for centripetal, of course, and this is equal to v squared over r. And this v is your regular v, your regular straightforward v, just like the one I gave you here up in the example. Okay, so I gave you everything we needed in our example up here. So the centripetal acceleration is 10 squared. Our velocity is 10 meters per second, so 10 squared divided by r, just the radius, and that's 4. So 10 squared divided by r, 10 squared divided by 4, that should be 25 meters per second squared. Okay, so really want to emphasize something here, that we already said our speed is constant, right? So that means our acceleration is 100% purely just because we are changing direction. So what does that mean? That means centripetal acceleration is not the same as regular acceleration or angular acceleration. It is its own thing. AC, it is its own thing. And because of that, it should not ever be used in any of the kinematics equations we looked at a few minutes ago. Not the regular ones, not the rotational ones. This AC is its own thing. Do not use this A, the AC, in any of the kinematic equations. Okay? All right. Oh, that picture didn't show up. Okay. This last page is just a quick summary of the equations that we talked about today. Oh, there it is. And I'm not really putting the slide here really to go through it. This is just so that maybe you can take a picture of it with your phone, so that as you're trying to do your homework and stuff, that you don't have to be going back through the video and trying to find all the different equations in all the different spots. This way they're all in one spot for you. They're right here. Okay, take a picture of this. And just want to remind you, this AC right here does not belong in any of these equations up here. None of them. It is its own thing. Okay. Other thing I wanted to mention here is I didn't really put this equation up before. Delta D equals delta theta times R. And this is just basically the conversion that 1 revolution is 2 pi radians. 1 revolution is 2 pi radians. And this is just if you want to convert regular distance to angular distance. And it seems like, well, why would you give me this equation that, like, right at the end and we didn't really talk about it? Well, if you think about it, we kind of did, right? Circumference is 2 pi r, but circumference is just around the circle one time, which is why we have 2 pi instead of a variable here. So it's really the same thing as circumference equals 2 pi r, just for any distance around the circle. C equals 2 pi r is only for one trip around the circle. This equation will be for any did you go maybe you only went halfway around, or you went 2 times around, and you want to know how far you went. It's kind of like that. We kind of did an example of it without using this actual equation on the angular distance slide. I think that was the second or third one. Okay, and just taking that example and putting it into an equation for you. Okay, so you've got a little bit of homework. Some of it's on Brain Genie. I do have a couple questions posted on AP Classroom as well. Just want to give you a tip about that. The graph ones, you just got to go back to your regular kinematics and look at what do the graphs mean, because they mean the same thing for angular stuff as they do for regular stuff. For example, if you look at a distance time graph, the slope is your velocity, okay? And it doesn't matter whether you're talking about regular velocity or angular velocity. If you look at a distance time graph, the slope is always velocity. Just which kind are you talking about? Doesn't matter. And then for a velocity graph, if you look at a velocity time graph, the slope is your acceleration, okay? And the area is your displacement, okay? And that's still true. It doesn't matter that we're talking about rotational stuff. It's still true. It's the same idea. So if you are having trouble with those, go back and look at your graph notes from when we did kinematics graphing, okay? The other homework that you have is just 3 problems out of your textbook. Those are on page 276. I just want you to do numbers 19, 17, and 21. And I want you to do them in those order, because that goes, 19 is actually easier than 17 is. 19 is really straightforward. You only need 1 equation. Number 17, you need to use 2 equations. You just got to find angular acceleration first, and then you can use another equation to get the how many revolutions it went through. Little tip on 21. So the disks are not going to be spinning at the same speed. It's not like both disks go around twice in a minute or anything like that. But the connection between the 2 disks is that they do have the same linear velocity. So they will have not the omega, but the regular v. They will have the same v. So you need to use what they talk about in the small disk to get the regular v. And then that's regular v also goes with the big disk, and you should be able to figure it out from there. As always, let me know if you have any questions. Feel free to email me, please, at any time. If you have questions, just send me an email. I'm here to help. Okay, so email me if you got questions. All right. Okay, I think that's all we got for today. I hope you have an all right time with your homework, and hope everybody's doing all right. And I'll talk to you next time.